Bismillahirrahmanirrahim. So, our today's topic is basically related to the wireless propagation and the challenges that are associated with the wireless propagation. So, let's start with some basic definition of radio waves. The radio waves are the type of electromagnetic radiations with wavelength in the electromagnetic spectrum that are not longer than the infrared light. Radio waves have frequencies as high as 300 gigahertz to as low as 30 hertz, right? So this is sort of a terminology, radio wave, that is generally used by a lot of people in the EE domain. So you need to know what radio waves actually mean. So at 300 gigahertz, the corresponding wavelength is 1 millimeter. So as you note that frequency and wavelength are inversely related to each other. So when you say 3 gigahertz, it means the wavelength is 1 millimeter. At 30 hertz, the corresponding wavelength is 10,000 kilometers. So like all other electromagnetic waves, radio waves travel at a speed of light, and that is in vacuum. Radio waves are generated by charged particles that undergo acceleration, such as time-varying electrical currents, and naturally occurring radio waves are emitted by lightning and astronomical objects as well. Radio waves are generated artificially by transmitters and received by radio receivers using antennas. So you need to know a bit of antennas as well. This is very important. Radio waves are very widely used in modern technology for fixed and mobile radio communication, broadcasting, radar and radio navigation systems, communication satellites, wireless computer networks, and many other applications. So different frequencies of radio waves have different propagation characteristics in the Earth's atmosphere, and long waves can diffract around obstacles like mountains and follow the contour of the Earth. Short waves can reflect off the ionosphere, that is a layer that you see when you look at the sky, and there is a certain distance at which you say that the ionospheric layer is there, and it runs to Earth beyond the horizon, while much shorter wavelengths bend or diffract very little and can travel on a line of sight. So their propagation distances are limited to the visual horizon. We will see shortly what this diffraction and scattering means, because this is actually what our topic is all about. So let's start the challenges of wireless propagation. A wireless channel is a hostile channel. Hostile is, I think, a pretty harsh word, but this is what the channel is all about. A channel actually changes whatever comes in its way. And that is why we have used the terminology as hostile. A wireless transmission might involve the line of sight communication or the non-line of sight communication. Wireless channels are random and often time varying. So wireless channels are random and often time varying. Your model can change with time. And this is also frequency dependent. So whenever you transmit a signal from the transmitter to a receiver, so in between transmitter and receiver, you have something known as channel. And as you have just seen that terminology of hostile is being used for channel, because the channel changes the transmitted signal. And hence what you receive at the receiver is not the exact copy of what was transmitted, because the channel does so much to that signal. So you can say that, for example, you start traveling from your house to a far-flung place that is, say, 20 kilometers away from that. So you're passing through different kinds of terrains, and you will feel the heat of the environment. And eventually, when you will reach your destination, obviously, you will not be exactly how you initiated your travel, because you got the effect of the channel, right? So this is a sort of analogy with yourself or the travel. But think about the signal. Signal is, you cannot even see the signal. Obviously, that is very weak. It has very weak power. and it has to go through a lot of different things. You will see today that what kind of role the reflection, diffraction, and scattering plays in this regard. So obviously, the signal undergoes so much to it that eventually the channel, you can say, it destroys the signal. So eventually, you have to do something at the receiver, and that is why the design of the receiver is always difficult. Okay, now we have seen that wireless channels are random and often time varying. So with time, they also change. It's not that they are static in nature, they change with time. Your model can change with time. And also, the channel is frequency dependent. For example, a channel behaves differently at, say, frequency f1, and the same channel may behave differently at, say, frequency f2, and it may behave differently at, say, frequency f3. So wireless channels are random and also frequency dependent. So you need to know these things. Modeling wireless channels is one of the most difficult part in wireless system design. So whenever you say wireless system design or wireless networking, it is the channel that is the culprit, and it is a channel that needs to be taken into account for your whatever kind of design you're making. Propagation basics: movement of electrons creates electromagnetic waves which can propagate through air. If an antenna is attached to a circuit, we can transmit and receive electromagnetic waves. So these are some of the propagation basics that I hope you know these things already. Now, the properties of radio waves, these are easy to generate. They can travel long distances. They have very high penetration. They can be used for both indoor and outdoor communication. Omnidirectional antennas can be used, and they can be focused narrowly at high frequencies. They are frequency dependent, as we have just seen. At higher frequencies, they act as light, difficult to pass through obstacles. They can get absorbed by rain, and they can subject to interference from other radio waves and sources. So these are few of the properties of radio waves. Usually channel models are statistical in nature. So whenever we use the word statistical, it means sort of probabilities involved. So if you just open the book of wireless communication, say the most famous book of wireless communication is that of Andrea Goldsmith. And if you just skim that book, you will see that it appears to you that more than 70% of the book is about the probability. So when you initially studied the probability, you were just looking at things like tossing a coin and things like that, playing with the cards. It's not like that. That was just the initial course of probability. Actually, probability has huge applications, and it has a very significant role in the present world that we are living in. So channel models are also statistical in nature. So they have sort of probabilistic involvement in them, and statistical modeling is usually done based on the measurement data for intended communication system and also for a frequency band. When we say coverage area, the coverage area can be changed with playing with different antenna parameters, for example, tilt, height, etc. So the coverage area can get changed. For example, there's an antenna installed and you just tilt that, the coverage area can get changed. So three main mechanisms behind electromagnetic wave propagation. So now we're going to study the three main mechanisms behind the EM propagation. The first one is reflection, a very common term that you have been using for quite a while. And reflection can be, say, from the ground, from the building, from the walls. Then we have something known as diffraction. This is because of the edges of the buildings and hills. So we're not talking about a massive chunk or a building. Rather, we're talking about the edge of the building. So in that case, we will not say a reflection has taken place. Rather, the diffraction is the mechanism that would be caused because of that. And then we have something known as scattering. And scattering is because of the rough reflecting surfaces. So you can say that by reflection, we mean something that has a bigger mass or a bigger size, then diffraction is because of something that has a smaller size, and scattering is because of something that has even smaller size. And this is sort of rule of thumb, but again, scattering by default, you have to say that this is because of the rough reflecting surfaces. And we will talk about these three shortly. But before that, let me talk about this fading. You have seen this terminology quite often, fading. Whenever you say that something has fade, it means the original shape or the original structure is no more, right? So this is what the fading is all about in terms of a general word whenever we say fading. So when we say fading in the context of communication, it means the signal strength or the quality of signal is compromised in that case. And then we have two types of fading. One is the large scale fading and one is the small scale fading. So propagation models generally focus on the average received signal strength at a given distance, and that is large scale fading. I repeat again, average received signal strength. Average is an important word over here. The average received signal strength at a given distance, that is the large scale fading, and the variation of the signal strength in the close proximity to a particular location, that is a small scale fading. So small scale fading can cause an attenuation of around 30 to 40 dB when the user moves by a fraction of a wavelength. I'm pretty much sure that you must have come across situations that you receive a call and then you move a little bit and then you get the signal strength back. That is a small scale fading, right? So just by moving a very small distance, you get the strength of the signal back to you. That is the phenomena of the small scale fading, because the signal strength or the variation of the signal strength is in the close proximity to a particular location. That is a small scale fading. But in case of large scale fading, moving a smaller distance will not work, because large scale fading means greater distances. So the situations in which you receive a call, it appears to you that the quality of signal is not good. You move a little bit and then you say, yes, the quality is restored. That is an example of the small scale fading. For a large distances, the average power gradually decreases and the average received power is predicted by the large scale fading. So look at this figure. This is the large scale fading versus a small scale fading. So on the x-axis, what you see is the TR separation. TR separation means the transmitter receiver separation in meters. Transmitter receiver separation in meters, and on the y-axis you see the received power. So you can see the line in the middle. That is the phenomena of the large scale fading. Even by moving considerable distances, the average power is almost the same. You can see that the average power, if you just follow the cursor of the mouse, the average power is almost the same in this case, this the line in the middle. But as far as small scale fading is concerned, on top of this line, you see variations which are of significant value. Variations, for example, this peak and this peak, there's a huge difference between them. There's a difference of like 10 dBm, which is very significant difference. And just by moving, you can see less than 1 meter, you see a significant drop in the signal strength. So this is the example of the small scale fading, whereas the line in the middle is an example of the large scale fading. Very important equation, and I will like every one of you to memorize this equation, because this equation is very important. This is known as freeze space equation. What it tells us is the received power at some distance d is equal to the transmitted power multiplied with the gain of the antenna, multiplied with the gain of the receiving antenna, multiplied with the square of the wavelength, divided by a constant 4 pi square of the distance, and L. So the gain of the antenna is given by 4 pi AE over lambda square. The effective aperture is related to the physical size of the antenna. You can say that this AE basically means the size of the antenna. For now, you can say that this means the size of the antenna, right? So effective aperture is related to the physical size of the antenna, right? So this is known as the gain of the antenna. An isotropic radiator radiates with unit gain in all directions. So for an isotropic antenna, you don't have a gain in a particular direction. In all of the direction, the gain is constant, right? And that is typically used as a reference in wireless systems. Effective isotropic radiator. Okay, before going on to the this effective radiated isotropic radiated power, let me tell you what isotropic antenna means. Isotropic antenna means an antenna that propagates equally in all directions. That propagates equally in all directions. So I have made this circle to show that if there is antenna in the middle, if there is antenna in the middle like this, so in all direction it has equal gain, or you can say the equal power. Let me repeat that gain is not a measure of the power. It does not indicate power. It's sort of a reference term, right? So gain for an isotropic antenna, it means in all of the direction the gain is equal. But in case of a directional antenna, it has a gain in a particular direction. It has a gain in a particular direction. So this is an example of isotropic antenna. When we say that we have a directional antenna, so in the particular direction, the lobe of the antenna would be look something like that. So this extra length that you see in the beam, that basically defines the gain. So this is sort of an example, a rule of thumb, or a quick reference to what gain actually means. So gain is always in a particular direction. So this is what a beam pattern of a isotropic antenna, and this is a beam pattern of a directional antenna. And that extra beam, or the extra strength that you see, that basically defines the gain of the antenna. And the greater the gain, obviously the better the directionality of the antenna is, right? Right. So we have effective isotropic radiated power, a very important parameter. And effective isotropic radiated power is the product of the transmitted power and the gain of the transmitter. The propagation, the power in the transmitted signal multiplied with the gain of the transmitter. That is effective isotropic radiated power. Okay. A very small example. What is the far field? What is the far field region? What is the far field region for a base station antenna with the largest antenna dimension of 0.5 meter and operating in both 9 megahertz and 1800 megahertz band, right? So very easy question. Lambda is equal to speed of light divided by the frequency. So you need to know what wavelength is. Wavelength is C over F. Lambda is equal to speed of light divided by the frequency. So the wavelength in this case is 0.3 meter, 0.33 meter, right? So first of all, you need to know what we mean by far field region, right? So this is a new thing you're experiencing right now. Far field region means a region which is far away from the antenna. A region which is far away from the antenna, so that the wave itself starts to look like a planar wave. It looks like a planar wave. So it originates from the antenna. It originates like this in the form of a ripples. In the form of the ripples. Obviously, we are not going into the details of antenna theory, but as you move away from the antenna, from far, the waves appears to you as if they are planar in nature. And the formula for that is this: 2d square over lambda. 2d square over lambda, that is the region beyond which you say that you have reached the far field region. You have reached the far field region, and that region is also known as the Fraunhofer region. The Fraunhofer region, that is also called as Fraunhofer region. For 18 megahertz, you see that lambda is equal to C divided by F, that is 0.17 meter. In that case, the far field region comes out to be 3 meter, where this D is the largest antenna dimension. That is the largest antenna dimension. In that case, the far field region comes out to be 3 meter, right? So let's move on to the next example, and this is very important. For a base station, let the transmitter power be equal to 50 watt. Okay.